Thank you. I would like to speak about bosonization, and I will shortly explain what I mean by that exactly. Let me remark that papers whose results I'm going to talk about were written with 3 people that are shown on the screen, and they are also parts of roughly 1/2 of my PhD thesis. So this is the outline of my presentation. So first I want to explain and motivate what I'm going to talk about, and then I would like to remind you about some certain ancient technology called Jordan-Wigner transformation, and after which I will move on to the bosonization method that I worked on, and perhaps at the end I will speak very briefly about some other approaches to bosonizations that have been developed relatively recently. So this is in gray because there might be not enough time for that. So first, the motivation. So as you well know, fermionic fields have the unpleasant feature that they do not commute even if they are placed at very distant spatial locations. So this is first of all counterintuitive, and also it leads to practical problems. So another aspect of the same phenomenon basically is that the Hilbert space of a composite system is not the tensor product of Hilbert spaces of constituent subsystems. It is something called graded tensor product, but these are more complicated, so to say, sometimes. And
can I ask?
Yes.
I mean, is the problem practical or philosophical? I mean, more practical than philosophical, or more philosophical than practical? I mean, it's sort of commutation, anti-commutation. It's just a sign, you know. Is it really such a big issue, or so maybe the problem is more like I want to be able to compute on the computer, and then anti-commuting stuff is unnatural. I want commuting stuff, or what is your opinion on this?
Yes, so there are several motivations actually. So first of all, there are these practical difficulties that you referred to, and I might mention a bit more of that later. So bosonic fields are sometimes in certain approaches just easier to handle. That's one thing, and another thing is that for bosons, semi-classical considerations are much more natural, and so sometimes it is easier to. So, for example, if you have something like spontaneous symmetry breaking, then if you have just a scalar field, then you can imagine that the scalar takes on some value, and but for fermions it's a bit trickier. So and also bosonization is an example of duality. So dualities are quite interesting and useful. So they sometimes lead to various insights. So it is good to have sort of alternative descriptions of the same thing often. So so these are the main motivations, and now I would like to tell you what exactly I mean by fermions. So I'm going to talk about lattice systems. So there will be some lattice lambda, some discrete grid of points, and it could be a triangulation or not necessarily triangulation, but some cell structure of some manifold or something like that, and by default these lattices will be finite, and one can also talk about infinite lattices. but I don't want to do that too much because that's much more technical. One has to fight through some subtleties with operator algebras, and so I might mention that once in a while.
Question.
Yes.
Did you say something about which dimension?
No, so the dimension is arbitrary. So this lambda could be basically anything, by default finite, but it could be like a cubic lattice in any dimension, either with open or periodic boundary conditions. It could be a triangulation of some manifold of some complicated topology. It just doesn't matter at all. The points of this, every point of this lattice hosts some number of fermionic operators, and fermions, of course, satisfy anti-commutation relations. And some of you may be more used to creation and annihilation operators, but it is actually in many contexts, and here also, more convenient to use self-adjoint fermionic operators, which satisfy anti-commutation relations like written here. So they are sometimes called Majorana operators in the literature, which has nothing to do with representations of Lorentz group whatsoever. It's just name, and basically because they are real. So every lattice site hosts some self-adjoint operators psi alpha, which satisfy anti-commutation relations. And this index, the range of this index alpha in principle may depend on the site in this approach. So of course you can imagine something like a very regular lattice, like a cubic lattice, and the same number of fermions on every lattice site. That's of course interesting, but such assumption will not be needed. So I'm not going to make it. And one very important feature of fermions is that there is a symmetry called fermionic parity, which takes every psi alpha to minus psi alpha, every fermionic field to minus fermionic field, and only operators invariant under this symmetry, also called even, are observable. And as far as I know, there is no process in nature which violates this sort of symmetry. So we don't need to. So the class of models that I'm talking about doesn't need to have any sort of conserved number of fermions, for example, number of particles operator, but there is a conserved number of particles mod 2. And
what about anyons? What about anyons?
Anyons?
Yeah.
What about them? So
you're not interested in anyons?
Well, I am interested in anyons, but I'm not going to talk about them in this talk.
I mean, it's hard to make an anion formalism
right.
when the whole point is that it's supposed to be independent of dimension, right?
Right.
The whole construction goes through
right.
for all dimensions.
Right.
That's the whole point, right?
Yes. There is some connection to anions actually, but let me not go into that now. Now, what I mean by bosonization. So what is the goal? The goal is to obtain an equivalent spin system, and by a spin system, I mean a lattice model which has a finite dimensional Hilbert space on every lattice site, and some operators or fields, if you like, on every lattice site, and fields placed on different lattice sites are supposed to commute rather than anti-commute with each other. So that is the goal. So since the Hilbert spaces on every lattice sites are not well, they are finite dimensional, so they are not. So in a sense, it's not really a boson. There is no canonical commutation relation or something like that. But the property that I'm after is that fields at spatially separated points commute. So first let me review this Jordan-Wigner transformation, which was introduced in 1928, so quite a long time ago. Let us suppose that this lattice lambda is just an open chain, so some L points arranged in a chain, and each point of the chain hosts some number of these operators psi alpha, which is even. So I'm making an assumption that the number of Majoranas per lattice site is even, and one can define these operators. First of all, some gamma of x is just the product of all fermionic operators at the given lattice site up to some phase, and then gamma with an index alpha of x is just the product of psi alpha and all of these gammas that I defined previously on sites before the given site, right? So I have some interval of points, so the points are ordered. So this makes sense. So
this operator is non-local. The gamma alpha. It depends on all. I mean, half of the whole lattice somehow.
Yes, you are right. So gamma alpha depends on the fermionic field non-locally.
Yeah.
And we have the following properties. So this gamma alpha and gamma beta on the same lattice site satisfy the same commutation relations as gamma matrices that everyone knows and loves. But on different lattice sites, these gamma matrices just commutes.
And is 1D now?
It's 1D. Yes. Yeah. So this is and the geometry is just a chain for now. So a finite set of points arranged in an interval. So it's a discretization of an interval, if you like.
And this follows from the elementary anti-commutation relations.
Yes. This is just an elementary calculation. What is sort of crucial here is that so first of all, the relation between these psi alphas and gamma alphas is invertible, so it is easy to express fermions in terms of these gammas, and furthermore, this relation is non-local, but this non-locality cancels in even operators. So if I take any product of two operators well placed at some sites x and y, two fermions at some x and y, then most of this non-local product will cancel because it will appear in both operators, and the result of such a multiplication will involve only operators which are on the interval between x and y. So so the non-locality cancels, and one can repeat the same thing for closed chains, so discretizations of a circle, and it is very similar, although as you note, there was some ordering of points, which is sort of unnatural, and one has to choose somehow the first and last point, and really think what's going on with boundary conditions. So it turns out that the boundary conditions for this gamma alpha, this spin, these bosonic operators, depends not only on the boundary conditions for fermions, but also on the value of this operator -1 to the f, which is the product of all of this gamma of x. So basically, the product of all fermionic operators in the system.
So if you have closed boundary conditions, then you could think of operators with a beginning and an end. You know, multiplying all sides from some place to some other place. From
yes.
X to Y. And you know, starting at number 1 is not different from starting at number 5 and defining things. Or do you really need to say this is the beginning and I'm defining everything starting from this place, and then using only those kind of operators, or are you just treating them democratically?
No, as far as I know, there is no way to treat them democratically. So you need to say which lattice site is first and which one is the last,
okay.
and you use this formula.
But
and now, so if your initial fermions have some periodic boundary conditions, then what does it mean? It means that there is some formal symbol psi L+1, which is just identified with psi1. But such identification is sort of so if you look what should be gamma L+1 here, gamma at the site L+1, then it will involve not only this psi but also this whole string. So this is the reason why this product of all these gamma operators actually comes up in the boundary condition. So one can treat all boundary conditions and all values of -1 to the f. But at the bosonic level, the boundary condition depends not only on the boundary condition of fermions, but also on this -1 to the f, which is sort of fun. And we will see a more complicated version of such a thing later on. So in higher dimensions, this approach fails because the non-locality does not cancel in even operators. So one can repeat the same thing, just one can always choose some ordering of points, call them the first, second, and third, and formally use the same formulas, but there will be no cancellations. So therefore, if one starts from some Hamiltonian for fermions, which is even.
But the ordering in higher dimension will be a little bit weird, right?
Yes, it will be very unnatural, and that's the point essentially. So there will be you can choose it somehow. But it doesn't give you anything interesting because the mapping that you will obtain will be very non-local. So starting from a local fermionic Hamiltonian, you will get some very non-local spin system, which is presumably much harder to study than the original fermionic system. So it's not useful most of the time. Okay, so I want to tell you how to overcome this difficulty and how to define a different mapping which will work in any dimension. So there was this paper in 82 that proposed that the following approach. So we bosonize even operators. We want to bosonize even fermionic operators, express them in terms of some spin operators, but instead of writing down the relation explicitly as it is done for the Jordan-Wigner transformation, just try to match commutation relations. And such matching of commutation relations was performed, and some concrete mapping was proposed. And this paper was basically unnoticed, and its author also didn't pursue it further, and there were some unanswered questions there. And so many years later, my colleagues and me, including the author of this paper from 82, revisited this, and we developed this further and proved that various expected properties are indeed true, and found new. Well, we developed it, and I will present the present status of this. So I will not go through historical route, but what should be mentioned is that in the last 20 years or so, bosonization was considered by many authors and in many different fields, and certain ideas were invented multiple times. So some of these things so for example, the original motivation of this paper in 82 was lattice quantum chromodynamics and attempt to simulate lattice QCD. So there are problems in Monte Carlo simulations, difficulties if one has fermions in the theory. So that was the original motivation. But later people considered a similar problem, in the design, for example, in the design of quantum algorithms. So let's say that you have bosonic qubits. how do you simulate a fermionic system with bosonic qubits? And there were also studies in the field of topological phases of matter. So various people used different languages, so they couldn't read each other's papers efficiently. So they invented stuff over and over again. So, but okay, let me move to the construction. So first, some justification of this algebraic approach. So I told you that we are matching commutation relations. The justification is as follows. So there is some algebra of even fermionic operators. It's a sub-algebra of the algebra of all operators, linear combinations of products of basic fermions. And this algebra has the following property. So this is just a simple algebraic fact. Every algebra of every representation of this algebra is a direct sum of irreducible representations, and moreover, there are only two irreducible representations up to isomorphism. And these irreducible representations are just the even and odd subspaces of the Fock space. So the algebra of the whole algebra of fermionic operators has only one irreducible representation, and that is the Fock space. But in the even subalgebra, we don't have operators which map between even and odd sectors. And therefore, the even and odd subspaces are representations on their own, but they are the only ones. One can show that.
Okay, so the when you say the algebra, you mean the algebra of even operators?
Yes, so I briefly mentioned also the algebra of all operators, but yes, but even operators are, so what are even operators? Either they can be defined as these operators which commute as -1 to the f. But any such operator is just a polynomial with terms only of even degree in fermionic fields. So this is the even algebra. So these properties, these facts mean that if we find a representation of this even algebra, it must be the Fock space. Perhaps up to restrictions on this -1 to the f. So it might happen that we only get 1/2 of the Fock space, and maybe there could be some multiplicity. Maybe a representation could have several copies of this irreducible representation. So in order to find representations, it is convenient to use some generators of this even subalgebra. So what I mean by generators, so there are certain operators which are here denoted S of E and T alpha of X, such that every element of the algebra can be written as a polynomial in these elements. And what are these generators that we use? So first of all, for every lattice site, I choose some special value of this index alpha, which is distinguished. So there is some asymmetry built in the mapping that I'm constructing. So I treat this special value alpha equal to 0 in a distinguished way. And for every edge of the lattice, I consider the product of psi 0 at the two endpoints of the edge. And for every lattice site and for every index alpha different than 0, I consider the product of psi 0 and psi alpha at this lattice site. So these operators are even, and I claim that every even operator can be expressed in terms of this SE and T alpha. Is the statement clear? Okay, so now let me write down. Let me tell you a bit about relations satisfied by these generators.
I guess it's because the psi 0 squared is 1 or something like that, or
psi 0 squared is 1. That's true.
Yeah. So I guess what you're, if we forget that psi is a Grassmann odd number, then we're basically doing Clifford algebras.
Yes, the fermionic algebra is definitely a Clifford algebra. Yes.
Yeah.
Okay. So these operators square to -1, and they satisfy some So they always commute and anti-commute. And I displayed this formula in order for you to see it once, but you should not try to memorize it. It doesn't matter for the rest of the talk what these relations look like exactly. So the important point, so these operators always either commute or anti-commute, depending on the geometric arrangements, and they can only anti-commute if the corresponding edges or lattice sides are close to each other. So when they are geometrically far, they always commute. And these relations are obtained by some simple calculations. So there is one more relation, which I will call a loop relation. So whenever these edges E1, there is some sequence of edges E1 to En, which form a closed loop, then the product of this S of E's is just equal to 1. And if you multiply this S of E's out, you will see that since psi 0 squared is 1, then all these psi zeros will just cancel, so you will get 1. So, of course, I'm using some specific operator ordering convention here. If you use different operator ordering convention, then you might get a minus sign, but with my convention, it is just 1. Now there is a statement which is not entirely obvious, but it has been proven that all relations between this S of E's and T alphas of X follow from the relations that I displayed on the previous slide. So to check that some relation holds, it's easy because one just has to multiply things out and you see that it holds. But the point here is that there are no other relations, essentially. Every other relation follows from this that I wrote down. And this means that we can define a representation of this even algebra in the following way. We construct some operators S and T alpha, and we verify that they satisfy all these relations. And then we will have a representation of the even algebra, and therefore, by the previous remarks about representations, we will know that the space on which the operators act can be identified with some direct sum of some subspaces of the Fock space. And one can, of course, understand this decomposition in the concrete construction that I will show you. So furthermore, I would like to mention that these loop relations are not all independent. So there is such a relation for every loop, but in fact, it is sufficient to verify them for elementary plaquettes. So what I mean by plaquettes, so for example, if you have a cubic lattice, these are just squares, like small squares formed by 4 edges, which are close to each other. So this is a completely local thing, in a sense. But if the topology of the lattice is non-trivial, for example, if one considers discretizations of a torus or something like that, then there might be non-trivial loops, which cannot. So non-trivial in the sense that they are not the boundary of some surface precisely. For these loops, this relation is independent of this plaquette, so it is an additional relation. So one has to check these plaquette relations and also these additional loop relations corresponding to non-contractible loops. And now I'm going to move to the spin system that achieves this bosonization that is desired. The system is defined as follows. So at each lattice side, we will have some gamma matrices, and there will be gamma matrices of 2 types. The first type has the matrices of the first type are indexed by edges which are incident to X. So there are as many gamma matrices like that as the neighbors of the lattice side. So for a cubic lattice in D dimensions, there are 2D matrices like that. And furthermore, there will be some second type of gamma matrices denoted with a prime, which have indices alpha, where alpha is not equal to 0. So there are as many of these as we have fermionic modes on the given lattice site, -1, because this distinguished fermionic mode with index alpha equal to 0 is ruled out because, well, it's treated in a different way, so to say. And gamma matrices at different sites commute. So again, we have some Clifford algebras, but at every lattice site, an independent Clifford algebra. There is no anti-commutation between gamma matrices at different sites. And well, but at the given site, we just have a Clifford algebra. So so the primed matrices and unprimed matrices anti-commute with each other, and yes, I think equations that are displayed are self-explanatory. And now we consider the following operators. So they have the same symbols as the fermionic operators, but with a hat, in order to remind you that it's not the same operator. It's an operator in this spin system. And first of all, so recall that S of E was sort of a hopping operator. It involved a product of two fermions at distinct lattice sites, psi-0 fermions. So S with a hat is now a product of two gamma matrices at different lattice sites. And this E appears as an index. So since E has this edge E has two ends, X and Y, then both X and Y host a gamma matrix which has E as an index, right? Because E is incident to X and Y. So
before the S matrix, that was the psi-0 in there, right? The psi-0x, psi-0y.
Yes. Yes.
But now it's a little bit different. Gamma has more somehow more freedom than just the psi-0.
Yes.
Right, because
yes,
it's not just about the site; it's also about the edge somehow. So before you had the gamma would be the same for each edge, and now it can be different for each edge, even if you are on the same site.
Yes. So this gamma E of X, I would like you to think about as something that lives at X, and E is just an index. So geometrically, it lives at X. Okay. So gamma E of X and gamma E of Y commute because they are at different lattice sites.
Yeah.
So this is the definition, and this T alpha hat is which. So T alpha was psi-0 of X and times psi alpha of X. So a product of two fermions at the same lattice site, and this will correspond just to this gamma prime with an index alpha. So these operators with hats, one can verify that they obey all of these relations that I showed to you earlier, except for these loop relations. These loop relations play a special role, and so they will not hold as operator identities, but they will be imposed on as constraints on states. And I will come back to this later, a bit later. Now, let me mention something.
So let me ask about that again. So the reason why the loop relation held was because in your multiplication, the psi-0 from one edge met the psi-0 from the other edge, and they squared to 1, right? And now it doesn't hold because you're going to have to multiply a gamma E with a gamma E prime.
Oh, well, so these loop relations only involve S's, so gamma prime will not enter at all. But
no. I mean, the prime is not on gamma, but on E. If I'm taking, gamma E1 with the gamma E2, that's what you're gonna
yes.
appear.
And so in such a loop, you will also find gamma E of X times gamma E of Y, but gamma E of X and gamma E of Y are different. So yes. So it just doesn't cancel. There will be different gamma matrices, and they don't cancel.
Right.
But if you compute this product on every side, there will be some even number of these gamma matrices.
Okay, and you're saying that you can use this to select states that are such that if that operator, which is not trivial now, it used to be trivial, but it's not trivial now, that would select put the states in two separate groups, one which is killed by that, and the other which is not.
Yes, yes. So there is some subspace in the spin system on which the constraint is satisfied, on which this relation is satisfied. It is not all state, but there are some special states on which this state is satisfied, on which this relation is satisfied, and this relation is actually in some suitable sense equivalent to the original fermionic system. So I will come back to this and make this slightly more precise later. Before I do that, I need to address another issue that appears.
But this, I mean, it sounds a little bit like gauge theory, where you don't impose gauge theory on the state, but you impose that some constraint that generates the gauge symmetry kills the states. But it's really quite a tricky thing. Usually you can't impose that the whole constraint kills the state, but you have to like take half of the constraints. You do some Fourier decomposition, and the positive modes kills the state, but the negative modes don't, or something like that.
Well, it's okay. So that's a bit tricky. So first of all, so in field theory, there are things like constraints of first kind and second kind, and they have to be treated in a somewhat different way. And so now I said that you impose something as a constraint on states, but a priori it is not obvious that any solution will exist even. So, but this has been checked, and I'm not going to go through all the proofs. I'm stating that you do that, but behind that there is some work that has had to be done to check that it actually works and that this is correct. So you want to know that solutions of these constraints exist, and then not only solutions of these constraints exist, but if you act with these operators S hat and T hat alpha on solutions of constraints, you don't go out of the constraint subspace. So on this subspace, you really get a representation.
Okay.
So yes, so this is something that not a priori obvious.
Yeah.
Definitely. Okay. So now probably everyone who has studied spinors in various dimensions knows that properties of gamma matrices strongly depend on their number, modulo 2 in particular. So this number of gamma matrices that we have at a site X is the number of neighbors of X plus number of Fermi operators at X minus 1. This minus 1 is because this alpha equal to 0 is treated in a special way. So we can consider the product of all gamma matrices at the given lattice site, and with some phase factor chosen so that the whole product squares to 1. And now if this n of X is odd, then in irreducible representations of gamma matrices, this gamma of X is either 1 or minus 1. And we have to choose one side somehow. So for example, 1. So we can just choose these gamma matrices in such a way that this gamma equal to 1 is just an identity, simple matrix identity. And there is another case where n of X is even. And then this gamma of X anti-commutes with all gamma matrices at X. And so there is no counterpart of such a thing in the fermionic system. And actually this describes a spurious degree of freedom at X. So this is again something that is not obvious at this point, but let me state it as follows. For n of X odd, one can check that if you follow the construction through, it works. So the bosonization works in this way. So now let's say that n of X is even. So we have this gamma of X which anti-commutes with all gamma matrices. So in particular, so we could think about this as another gamma prime alpha, corresponding to some another fermion which was not present originally. So therefore we can, in this system, we can bosonize some fermion, some more complicated fermionic system which has more degrees of freedom. If you don't need to think about it this way, but if you don't, you will just find that in the representation that was constructed, there is some high multiplicity. So of course the interpretation is that there is some additional degree of freedom. Therefore, for this reason, we restrict to the case that the number of neighbors of X is equal to the number of Fermi operators at X modulo 2. So then there are no spurious degrees of freedom, and yes, we have to. This is the case where gamma of X has to be chosen to be, let's say, 1. And one can also treat the case, the systems where this relation is not satisfied.
Wait. Now, can I ask? So this is really, now you can make contact to real fermions, right? Because if you have a square...
Excuse me, make contact to what? I didn't...
To real fermions, real fermion representations. If you have a square like this, you know how many neighbors you have depending on dimension. And you know the dimension of a fermion representation also depending on dimension. And is this always fulfilled? If you do that, if you try to sort of just discretize a standard Lorentz representation fermion in any dimension, does it work?
If you think about okay, so if you think about cubic lattice, then every side has an even number of neighbors, and this means that the number of these Fermi operators has to be even.
Yeah.
In this case, so then
and that's always true. Yeah.
So you have to have an even number of Majoranas. So this means that if you have some creation and annihilation operators, every creation annihilation pair is equivalent to 2 Majoranas. So this is true. But then you might think about, so there are several issues with this. So first of all, one could consider some Majorana fermions, and then maybe the answer is slightly different. And I cannot give you the full answer in any dimension off the top of my head. Another thing is that actually discretization of fermions is a touchy business, because if you discretize naively, one often finds and try to. So now we talk about discretizations of field theory. So you have to take some continuum limit, and what one finds is that if you do it naively, you can get some spurious degrees of freedom. So there is no simple correspondence between the number of operators at the lattice side and the number of degrees of freedom understood as I don't know, number of poles in some propagator in the continuum limit. So this is a delicate matter.
Okay.
But if you think strictly about lattice systems, then this relation is some restriction on the type on the class of systems that can be bosonized. And you can always think about bosonizing some system which has more degrees of freedom and maybe try to decouple them. I don't know, put some term in the Hamiltonian which makes them very heavy or something like that. But one can identify in this approach the spurious degrees of freedom, so this is possible to do, but this is some additional thing. So if you just want to follow the procedure directly, I don't want to have spurious degrees of freedom, then this relation has to be satisfied.
Okay.
And now I want to go back to the role of these loop constraints. So in this spin system, for any loop, which will be denoted by L, so L is some sequence of edges such that the initial point of the next edge is the final point of the previous one, and we can define these operators W of L, which are products of these S hats of E. So if there were no hats, then this would be just one identically, but the problem is that this is not one identically. It's some product of many gamma matrices. And what turns out is that these operators square to 1 and commute with each other, and all of these S hats and T hats. And therefore, they can be all diagonalized simultaneously. So there are some states psi such that W of L on psi gives some omega of L times psi, where omega of L is plus or minus 1, depending on L, of course. So there is a diagonalization like that. So we are after the states with omega of L equal to 1, because this is the relation that we have initially, that we have had initially for fermions. But actually, it is interesting that states with different omega of L also have some physical interpretation, and that is what I would like to explain next. So in lattice gauge theory, gauge fields are typically introduced on edges. And we consider a Z2 gauge theory with, so there will be some edge variables, A of E, which are 0 or 1. So, and group operation is just addition modulo 2. So of course, Z2 gauge theory is a weird thing from the point of view of continuum physics and field theory, but on the lattice, it's perfectly fine. We could consider some minimal coupling of this A to fermions. And if we do minimal coupling, then it means that for operators where there is some product, so let's think about the Hamiltonian, for example. So we want to modify the Hamiltonian so that it is depends on this H and on this A and is gauge invariant. So in every product of Hamiltonian of two fermions in the Hamiltonian, where the fermions are put on different lattice sites, we have to introduce this factor -1 to the A of E, where E is the corresponding edge. So I call this decorating or something like that. So the new Hamiltonian is the expressed in terms of these new operators, which I call S of S with the subscript A. It's just the same expression, but instead of S's, we use S of A's. So therefore, we introduce these new generators in the algebra. Instead of S's, we have SA's. And one can check that these operators satisfy exactly the same relations as the previous operators, but this loop relation is altered. So as the product of SA's along a loop is now just equal to the Wilson loop observable of the gauge theory. So the product of A of A is on all edges that make the loop, that form the loop. And therefore we have the following interpretation: states which satisfy these modified constraints, where you have some non-trivial omega of L here, correspond to fermions coupled to a Z2 gauge field, such that the omega of L is just the holonomy of this gauge field along L. And I would like to emphasize that in the spin system, in order to perform this minimal coupling, one does not alter formulas for operators. One just changes the constraints, and that is already responsible fully for introducing this gauge field, background gauge field, because it's not a, I don't think about it as a dynamical thing, it's just some fixed field. Is the statement clear, more or less?
Yeah.
Okay. So now I would like to describe the structure of the Hilbert space in this spin system that is used in bosonization. So I told you that one can diagonalize this W of L operators, which are now interpreted as Wilson loops of some Z2 gauge theory. All these subspaces have the same dimension, because we know that there is some operator which satisfies such commutation relations that it maps between different subspaces. So different subspaces corresponding to different gauge fields have the same dimension. And then by counting the dimensions, we can just by counting the dimensions, we can check that that dimension is exactly such that that every such subspace describes exactly 1/2 of the Fock space. So one possible value of the -1 to the F with multiplicity 1. And which value of -1 to the F is realized? depends on the geometry and the representation of gamma matrices that we chose. I remind you that there was some operator small gamma of x, which was the product of all gamma matrices on the given site, and we had to choose whether it is 1 or -1. So this choice has an effect here. And the funny thing is that in a given representation, there is some combination of which is a fixed constant, so it cannot be changed by acting with any operator. It is the same for all states, and this combination is -1 to the f times the product of -1 to the a of e over all edges. So this product is just a constant which depends on, so what is its value? It's 1 or -1, and what is it exactly depends on the geometry of the system and also on this choice of representation. But for a given, if we fix these things, then this is just one concrete constant, and it can be computed. But now this means that there is no way that fermion fields could be represented on the spin system, because fermion fields change the value of -1 to the f, but they don't change the gauge field. So the only thing that can be represented is an operator which creates a fermion, but also creates some gauge field. So every operator which creates or annihilates an even amount of fermions, even number of fermions is represented, but for just creation of one fermion, it always creates some lump of gauge field. So this is also sort of the reason why these basic operators in this system can be bosonic, because they do not create a fermion, they create fermion together with a gauge field. But if you think about well, exchange of two such things, then this exchange involves not only exchange of fermions, but also some Aharonov-Bohm phase, and therefore the total exchange could be bosonic. So
I mean, should I think of the gauge field as somehow gauging fermion number, or?
Yes, you should think exactly that.
Wow. Sounds cool.
So I'm almost done, and I'm actually slower than I wanted, but okay. I wanted to make some remarks about some specific features of various geometries. So first of all, about tori and more generally closed surfaces or closed manifolds. Typically there will be some non-trivial loops, and therefore in such a system, in this spin system, you have constraints which are non-local, which is sort of ugly. So non-simply connected case is a bit not nice. And you can also just ignore the non-local constraints, but then just impose the plaquette constraints. Then the Z2 gauge field is locally absent, but this global gauge field with some holonomy along non-trivial cycles is present. So it's a bit like summing over all boundary conditions then. Now you can consider open boundary conditions. Then you have some boundary, and let's think about some regular geometries like cubic lattice or something like that. Then the number of neighbors jumps down for lattice sites at the boundary. Right, so there is no edge sticking out of the lattice. And therefore this relation that the number of neighbors has to match the number of fermions may be violated at the boundary, and you can identify some spurious modes which live at the boundary. So there are some so to say edge modes that appear, but they can be treated, but one has to be aware of them. And
can you just eliminate some of the modes of the fermions at the boundary? You know, alpha was an arbitrary number.
Sure, but let's say that you have a concrete fermionic system, and there is some concrete number of fermions that you want, then you don't have this choice. So you have a choice what boundary conditions you impose on the spin system, but well, of course, if you are interested in some thermodynamic quantities, then maybe these choices don't matter, and there is. But I'm just saying that well, the boundary has to be treated in some special way. It is not true that you can choose any boundary conditions and not care what happens at the spin side, because then you will have additional degrees of freedom, basically. And I would also like to mention briefly the infinite lattice. And okay, so in the spin system, we can implement any even operator. So we can implement a string operator which transports a fermion from some site x to y, or y to x. Then you could think what happens when this y goes to infinity. So then you get some string operator, which is an infinite product of some spin operators. And some such infinite product. So first of all, it is not obvious what it means, because maybe it's ill-defined. So I don't want to go into gory operator algebraic details, but there is a way to make sense of such a thing. So such a non-local operator, which is an infinite product, but in general, it will map between different superselection sectors of the spin model. So if you have a system with infinitely many degrees of freedom, then it is a fact of life that it is no longer true that the algebra of local observables in your system has a unique representation. There are different representations, sometimes called superselection sectors, and this infinite product will map between different superselection sectors. So so then we have sort of a fermion operator in the spin system, but it is non-local. It is a string operator mapping between different representations of the algebra of observables. And I have some slides, so which I want to omit now, because mostly because in the interest of time, but I just wanted to mention one special case where you have a cubic lattice in dimension 2. And so in this case, we managed to actually solve these constraints, because in the spin system, there are some constraints. So what are the solutions? So we managed to write down explicitly solutions of these constraints. And that is achieved by mapping them to some well-known system called toric code. So probably some of you heard about it. So so that is some connections to onions that were mentioned earlier. But okay, I don't want to mention that. And this is my summary, and I'm just going to display it without saying all this, because I would like to end now. And thank you for your attention.
You can take a few extra minutes if you want. It's okay. You don't have to skip because of the time. It's just that some people had to leave, but if you want to take 5 minutes more, then it's okay.
Well, I always prefer to be on time, but maybe, okay, so let me just say this summary. So I described to you a procedure of bosonization in any dimension, in quite general geometries, in fact. It maps fermions to constrained spin systems, and constraints are local unless there are some non-trivial loops in the geometry. And these constraint operators that appear may be interpreted as holonomies of some Z2 gauge field that couples to fermions. And only even fermionic operators are represented in the bosonized systems. Operators which create an odd number of fermions necessarily also create some Z2 gauge field. And also there was this constraint that is interesting, that the number of Majorana operators per lattice site does not match the coordination. Sorry, I'm a bit tired. So the number of Majoranas per lattice sites has to match the coordination number, modulo 2. And if this is not satisfied, there are some spurious degrees of freedom, and one can understand them. And okay, that's all. Thank you.
Okay, thank you very much.
Thank you.
It was nice that you gave the summary. Yeah, I'm glad for that. So yeah, thank you very much for the talk. So if we have any questions, please feel free to unmute and ask.
Yeah, I'm muted. So did you also make numeric simulations using these ideas for some systems.
Well, so yes, so actually, let me first start by saying that there was this original motivation to hold this whole program of applying this to lattice QCD, but this has never been achieved so far. So there has been a huge progress in with Monte Carlo simulations with fermions, but using different methods altogether. So and still not every system is treatable. So so there were some. So some of my colleagues did some numerics to understand better these solutions of constraints, because already these states are quite interesting. I mentioned that they are not easy to write down explicitly. In the case where they can be mapped to some non-trivial system which has some so-called topological order. Besides that, we did not yet try to apply to run simulations where where you actually bosonize something, and no, I just we just did the general analysis, so to say.
Yeah. Okay. Another question. Can you give some explicit situation where you actually look at the theory with different number of fermions at different sites, so that the alpha changes? You know, the range of alpha changes. What would be? Why would I consider something like that?
Well, so first of all, in this situation with boundary conditions, which I mentioned, so this is sort of forced upon you because there appear these spurious degrees of freedom. So we wanted to formulate everything in such a way that they can be incorporated as. But most of the time, I guess, if you discretize, for example, a Lorentz invariant field theory, then I suppose this does not arise, at least in the bulk. But yes, I think it's just good to not make assumptions which are not needed for anything. But in this case, there is very little that you. So let's see. So in the first, some previous iterations of this idea, there was a version where this index alpha was just not present, and every lattice site hosted exactly two Majoranas, or rather, instead we used one creation and one annihilation operator, and so the number of neighbors had to be even always for every lattice site. And then we thought, first of all, can we do an odd, well, just one Majorana per lattice site, and can we do any multiplicity? And while developing that, we realized that it just doesn't matter that the multiplicity is constant. It just doesn't change anything in the reasoning. It's not made more difficult in any way, but you could regard it as something slightly artificial.
Okay.
So you mentioned that this hasn't been applied to lattice QCD yet, but do you expect that it can be and that it will help there, or is there a reason to think that it will not solve the issues that you encounter there?
So I'm a bit out of the loop right now. If as far as lattice QCD is concerned, I'm more interested maybe in applying this to physical situations, more in the direction of condensed matter physics, like the topological phases, and I do think that I think bosonization is a fairly natural question, and it will find its applications. I don't know if bosonization has developed here or so. Like these older approaches, like Jordan-Wigner transformation, for example, has countless applications. But of course, the problem with these higher dimensional versions is that they are more complicated. So you get more complicated bosonic systems, and another thing is that if you have a bosonic system, so we can map fermions to a local bosonic system, which is completely fine, but in general, understanding a bosonic system on a lattice is hopeless. So there are no numerical methods, for example, for a general bosonic system in any dimension, because things like tensor networks don't work very well in high dimensions, and Monte Carlo just most of the time breaks down because you have sign problems. So things like that greatly restrict applicability of this. But there were some works where people had some classifications of or proposals, at least, of classifications of some topological phases of bosonic matter, and they wanted to understand what happens if you include fermions. Are there additional phases? And they developed some. They used some bosonization, some different bosonization that I didn't. That was also developed just a few years ago.
Okay, do we have any other questions or comments? Okay, doesn't seem to be the case. So thank you again very much, Błażej.
Thank you.
And let's connect on my Zoom. I sent you an email. So
do you mind if I take like a 2-minute break? I will.
No, actually, let's take a 15-minute break, because I need to go to the bathroom and I need